Okay, so what we're doing conduction analysis. We're looking at this thing called an alternative method. But recall methods of conduction analysis, there are several. We have the heat diffusion equation. That's the big complex partial differential equation. You need to have boundary conditions. You can solve for the temperature inside of an object. And sometimes for certain shapes you can do analysis and solve that analytically, which we will be looking at later in the course. Numerical analysis, I've already talked about what we're going to be doing there. And we will look at numerical analysis, and I'll give you an Excel spreadsheet tool that enables you to do two-dimensional numerical analysis, but there are other techniques as well. And then finally, what we've been focusing on we did this last lecture, is what we call this alternate or alternative method. And essentially, it's using Fourier's law under some rather severe assumptions, but turns out these are pretty good assumptions because for many of the systems that we study, these assumptions do apply. So let me just briefly overview what that alternate method was and then what the results were, and then we'll move on looking at how to apply it for engineering problems. So if you recall the alternate method, we started with Fourier's law, minus Ka dt by dx. And if you know the area as a function of x, or it could be radial location as we saw for cylindrical and spherical coordinates, but if you know that, then you can make a substitution into Fourier's law. And then what we did is we rearranged that and we set it up to enable us to be able to integrate. But typically what we were doing is we were pulling the area over to the left-hand side in the denominator, and then we were left with minus k dt. This is where we said that we're going to assume that the thermal conductivity is not a function of temperature, so that enabled us to pull it out of the integral, which I'll show you in a moment. So we have qx. And we integrate from some boundary condition that we know what's going on to some x location that we're trying to figure out what the temperature is. And you divide that by a as a function of x. You pull k out of the integral from T1. That's the temperature at the boundary condition at 1. And then we have the integral dt. Now this works. It works subject to a couple of constraints. One of them, we had to have steady state. The second constraint that we had was one-dimensional. So that means that all the heat is flowing only in one dimension, not in 2 or 3 dimensions, which we'll look at later on in the course. Third one, no heat generation inside of the material that we're studying. And the fourth was that K is equal to a constant. So the thermal conductivity is not a function of temperature. And what do we get out of this? Well, you get T of X and you get Q of X. So we were able to get the heat transfer and the temperature profile. In terms of engineering, this is usually the one that we are most interested in because we want to figure out what the heat loss is. So what I'm going to do now, I'm going to summarize the 3 different systems that we looked at. And we looked at the plane wall. Well, it wasn't quite a plane wall. We looked at that example problem with a conical section, but this would be what you would get if you were to look at the plane wall. So I'll draw out a schematic. So that's a schematic. Now what we were able to determine was the temperature distribution. We were able to determine the heat flux, and So what we did for all three cases, we plugged Q of X into T of X in order to give us the temperature distribution in the solid. Okay, so that was for a plane wall. We also looked at a cylinder. So that was the geometry for the cylinder, Ri, R outer. And what we obtained here was the temperature distribution. And if you recall, for the cylinder, it resulted in a natural logarithm. We were able to solve for the heat flux. And just like for the plane wall, if you plug the heat flux into the temperature distribution, we were able to come up with the temperature distribution function in the cylinder. Okay, so that's what we got for a cylinder, pipe flow, and many engineering applications where we would have cylindrical coordinate systems and we're trying to determine heat loss. But that's what we got for the cylinder. And then finally, spherical. This might be something like a storage tank. You could have spherical coordinates. Okay, so that's a scenario for the sphere. Temperature distribution. And just like for the other two, you plug Q of R into T of R. And you get the temperature distribution in the wall of this sphere. Okay, so those are the three different geometries that we've considered. And the reason why I put them all out is because we're going to summarize them in the next segment. And what we'll do, we're going to look at the form of them. And it turns out that there is some sort of commonality to all three of the forms that we have here for both the heat flux as well as the temperature distribution. And so what we'll do, we'll come up with a shortcut method that enables us to analyze what is going on for heat transfer either through a plane wall, through a cylinder, or a sphere. And we'll be able to do more than just what we're looking at here. We'll be able to do scenarios where you might have a sphere with insulation on the outside of this sphere. So you might have some insulating layer, and then there might be convective heat transfer going on out here. So you have wind blowing, and that has an impact. We're going to develop a technique that will enable us to look at that, and that is referred to as being thermal resistances. So that's where we're going with all of this, in case you're wondering. We don't want to have to solve these equations all the time and write out all these different terms. We'll come up with shortcut methods. And that's why I said engineers are efficient. I said engineers are lazy, but that's not true. Engineers are very efficient. We like to find shortcuts and ways to be able to do things more effectively and efficiently. So that's where we're going in the next segment. We're going to work towards thermal resistances based on the results that we got thus far with this alternative method.